And let me introduce to you our next speaker, Huan Liu, also from the School of Physics at the University of Melbourne. And the title of her presentation will be Sketch and Peel, Neon Ion Beam Patterning of Black Phosphorus.
Hello, everyone. I'm Huan Liu, a PhD student in Professor Kenny's Crozier's group. Today, I'm going to introduce our recent work about the sketch and peel neon ion beam patterning on black phosphorus. Given today's topic is about direct light lithography, I guess neon ion beam is one part of focused ion beam lithography. And it's commonly used in metal material like gold film or gold flake. This is a previous work of our group, which used helium ion beam and neon ion beam unitedly to create a plasmonic nanotwister to trap nanoparticles. And today I'm gonna use this same technique to apply to a new material called black phosphorus. So black phosphorus is a quite popular 2D material recently. It has a monolayer crystal structure. The monolayer BP has a puckered honeycomb crystal structure, and the interactions between layers will lead a direct band gap of 1.7 electron volt. This will enable several electronic transitions between conduction band and valence band. And when we change the thickness of BP, the band gap can be tuned from 1.7 to 0.33 electron volts, which can cover a large infrared spectral range. This thickness tunable band gap is quite common in 2D material family, while what makes BP stand out is BP can maintain direct band gap in arbitrary thickness, which means it can give high PLQY, which is quite important to create a light emission device. The other interesting properties about BP is the anisotropic optical constant of the in-plane directions, and also the high refractive index in mid-infrared range makes it quite good material to provide better optical mode confinement. Based on BP's superior properties, many high-performance devices have been fabricated. For example, the high bandwidth and high specific detectivity mid-infrared detector have been fabricated before. And also the mid-infrared lasing by integrating BP flake with external optical design cavities. Laser emission has been realized in these systems. And also epsilon near zero property of BP in far infrared range has also been found recently, which is quite promising to realize perfect light emission absorber based on BP. So the capability to be able to nano-pattern BP will enable more exciting applications and provide better performance. But the challenge to nanofabrication on BP is quite vulnerable. It's easy to oxidize after taking out of the glove box. Previously, several works have been tried to nano-pattern BP or etch BP. The first one is using induction coupled plasma etching. They use argon or oxygen plasma to thin down the BP flake with a not too bad etching rate. However, the actual problem is it needs to combine with lithography technique, e-beam lithography or photon lithography. This long fabrication workflow will increase BP's chance to be exposed to the air and cause degradation. The second one is the people putting monolayer HBN on top of monolayer BP, and they use electron beam to directly open a narrow cut through the HBN layer. So the BP will be exposed to the air within that area and degrade. In this way, they create a narrow cut like down to tens of nanometers wide. Similarly, for the third one, they use AFM tip to scan over around BP region, and by applying a certain voltage through the AFM tip, the BP within that applied voltage will have a speed up degradation process. Then, after finished the scanning, they washed away those degraded BP particles, so they can create a defined structure like this checkerboard pattern. But the problem of these two techniques are they can only be applied to really thin BP flake, like atomic layer thickness or tens of nanometer. When BP gets thicker enough, the lateral resolution will be worse, like this. So we need to figure out a method to be able to pattern BP flake with a few hundred nanometer thick at least. Our solution is use the near ion beam nanopatterning facility in the MCFP Center of Uni Melbourne. And Dr. Anders Vallo, who sits behind there, is the manager of it. I guess the advantage of this, also the cool part of this facility, is the special design tungsten tip, which sits on top of this column here. It has a really fine design tungsten, like only 3 atoms is at the end of that tip. And when the neon atom or helium atom is surrounding this 3 atom here, it will be ionized, and under the acceleration electric field, it will form a stable ion beam, which can be used to pattern our structure. Because of this, the beam size is limited by the size of the tungsten atom, which is below 1 nanometer, and the divergence is pretty low after collimated. So we want to use this facility to do the high-resolution nanopatterning. So to investigate this technique on a new material, we need to do the dose test first. So we investigated the milling depth versus dosage curve by patterning an array of rectangle on one piece of BP flake with a thickness of 1.1 micrometer, and use AFM to characterize each milling depth for each dose, and finally get our milling depth dosage curve here. But after FIB patterning, we find a yellowish blood region surrounding this each milling rectangle, which could be the FIB-induced material damage. We want to minimize this damage when we fabricate the nanostructure. So consider we want to get an isolated structure. In normal FIB lithography, we need to remove all the material away from this structure, which is really time-consuming and will cause more material damage or redeposition. So instead, if we just sketch the structure by outlining the structure we want to make, and think of another method to remove the rest of the material, it will save us a lot of beam time and cause less material damage. So following this initial idea, we firstly investigated the resolution of just using FIB to sketch the BP. We produced a CMOS logo array with different sizes, and from the smallest logo and the zoom-in view of the letter T and M, you can see the FIB cut is quite narrow, around tens of nanometers range. After FIB sketch, we developed a technique which is called polyvinyl acetate-based peel-off process, which can be performed in conventional 2D material transfer station here. The workflow is, assume now we got FIB sketched BP flake. We drop cast a PVA solution onto a glass slide, and we flip the glass slide over with the PVA solution side towards our BP flake here. We can monitor the lateral position of the PVA droplet and BP flake from the top, from the camera on the top, and we move the sample and PVA solution relatively until the edge of the solution is partly contacting with the BP flake. We will maximize the contacting area and then wait the PVA solution to dry out. It will form an adhesive film. So then we move the sample away from the last light. So the PVA film will be adhesive enough to stick the BP flake, the surrounding part of the BP flake, away with it, leaving only the isolated central structure on the substrate. Following this workflow, we get an isolated koala-shaped BP flake, like here. And then we did the surface morphology characterization on this tiny koala from AFM. And we can see the thickness is around 700 nanometers. And from the side wall profile, it gives a quite vertical side wall, which is quite good. And next, we want to investigate whether this material is still in good quality after FIB fabrication. We firstly look at the Raman spectrum of this after FIB fabrication. We know that for crystal and BP, it has 3 characteristic Raman modes corresponding to 3 lattice vibrations. We call it AG1, B2G, and AG2 here. After FIB sketch, we probe the Raman spectrum of near the ladder T edge, the line here. The Raman spectrum shows an elevated baseline emerging within the BP mode region, indicates the amorphization of BP, which is a quite commonly observed phenomenon when performing FIB on other material like gold. But for BP, the amorphization actually can be removed by simply put the sample on a hot plate. Those redeposited particles, or say amorphized BP, can firstly be oxidized and go on a sublimation process and leave the sample surface. So after the simple treatment, we probe the Raman spectrum at the fifth edge again. We can see the elevated baseline disappears. We also plotted the Raman modes peak intensity mapping over the ladder T region. We can see for each Raman mode, the intensity is quite uniform with the ladder T region, indicates to well-preserved BP crystallinity. We also looked at the mid-infrared light emission out of the FIB sketched structure, because that's what's our next step. We want to use this kind of structure to modify the light emission property out of BP. So we firstly mount our sample onto 2D motorized translation stage. We excited our sample using 660 nanometer laser with a spot size of 5 micrometer. And then we move our sample in the XY direction so we can record the PL emission out of 5 micrometer size region and plot it as a function of XY positions. So we finally got the PL map. We can see the PL emission within the FIB sketched cut line is actually lower than the region which is far away from it, which indicates FIB did degrade BP a little bit. And after we peel off the BP flake, we can see a blurred emission area in a koala shape. And similarly, we perform the thermal treatment on this sketched sample. We can see a twofold PL enhancement within the koala. And from the spectrum and power-dependent PL measurement, we can see after thermal treatment, the PL intensity is actually retrieved to the level before any FIB fabrication. So for a simple summary, we developed the sketch and peel technique to create isolated BP structure. Accompanied by the thermal treatment, the properties of BP is well preserved. And this fabrication can cover a large thickness range from tens to hundreds nanometer thickness. Although it's a successful initial try to use this new FIB to BP, we still have some problem need to work out in the future. First, we only produce nanostructures in tens of micrometer size, and it already cost us like half an hour each also. If we want to do like large scale writing on this material to create some kind of 2D material integrated circuit, it will cost a large beam time. And for creating of isolated structure, an extra peel-off step is required. So if we can think of methods which can save us a lot of beam time, that would be. The second aspect is working on the material itself, because the BP flake we currently get is from mechanical extrusion. It has a limiting size of around 100 micrometer. So it would be much better if we can think of methods to grow this material into a wafer size scale. That's pretty this much of my presentation. Appreciate any further comments or ideas. So finally, I want to thank the members of our group, and also especially thanks to Dr. Anders Barlow, who contributes a lot to this project. Thank you.